Okay, well, let's get started. So the main topic today is going to be Venus. We actually have a little bit to finish up from chapter 8 on Mercury. So let's just start out with that. My microphone is back to the screen. Going down. Little gizmo disappeared. Okay. Okay, so we hadn't quite finished talking about Mercury a little bit, so I want to review a little bit here. So this is a shot of the Florida Basin from the 1970s Mariner mission. And then, again, we don't even see the entire feature here because Mariner flew by only one side of Mercury and didn't actually get a photo of the entire Florida Basin. But here's, this is a color-enhanced photo, I should say. Mercury actually still does look pretty gray, just like what we're seeing in this previous shot. But what was done here was topographical features were enhanced just to give a better sense of what we're actually seeing in terms of the geological features. But this is not actually true color. But still, kind of a cool shot. And again, the main reason I'm going back to this today is because I wanted to reemphasize that the impact that actually formed the Florida Basin deposited this very large mass in there, which apparently plays a key role in reinforcing the spin-orbit resonance that we see in the case of Mercury. Okay, so again, Florida Basin results from this huge impact. Just go back. So we have this huge impact coming in, and seismic waves going through and forming not only the Florida Basin, but this, what we call this weird terrain on the other side. I'm not too interested in that at the moment. But what we want to talk about is how this is related to the 2 to 3 spin-orbit resonance again. So I just want to review that because that's a little bit subtle and kind of an unusual thing that we haven't seen before. So when we look at the spin period and the orbital period of Mercury, we find that there's this 2 to 3 ratio. I'll go over. Every 2 years, we actually have 3 sidereal days. So this is the sort of thing that has to be reinforced by a physical effect. Something like this is not going to happen coincidentally. There's got to be a reason. Just like when we look at the moon, for instance, the moon keeps the same face toward the Earth. We understand that totally because it's an effect of the tidal force of the Earth acting on the moon. If the moon spun a little bit, then its spin energy would actually be converted into heat anyway, and it would eventually stop spinning with respect to the Earth. We're seeing something more complex here, because it's not actually a 1-to-1, it's a 2 to 3. So the idea is that there's a massive blob there, which points toward the sun at perihelion, and that massive blob is actually this. Sorry, hold my microphone manually here. It's the effect of gravity on this massive impact crater that's actually causing it. And again, the way that we even discovered this was using Doppler measurements of the rotation back in the 1960s, because up until then it was thought that Mercury actually was in a tightly locked orbit. Okay, so what we find is that instead of having a sidereal rotation period which is equal to 88 days, which would be the year on Mercury, that's 88 of our days, what we find is the sidereal rotation period is actually 59 days. So we have this unusual situation where we have a 2 to 3 ratio. Well, this is just looking back at the moon again. When we look at the moon, the spin period is the same as the orbital period, so it keeps the same face toward the Earth. But when we look at Mercury, Mercury is not keeping the same face toward the sun. Instead, what we find is the spin period is 2/3 the length of the orbital period. Not equal to 1-to-1, it's 2/3. And so what that means is that for every 3 spins, which are sidereal days, for every 3 sidereal days, there are actually 2 years on Mercury. And so that is, of course, kind of a somewhat difficult to understand state of affairs. And so let me just quickly go through this this summary diagram thing here. Sorry, I don't have enough hands to do everything at the same time. Okay, so we start with this idea that we have high noon. Now, this is also going to be in alignment with a distant star. So at time 0, our stick here, which is locked down to Mercury, is pointed to the sun, and it's also pointed at some distant star. Then we let the rotation proceed, and we have the counterclockwise orbit. And then, after 59 days, we re-achieve the stick pointing to the left, which means that that's 1 sidereal day after we started the process, because the sidereal day will be the time it takes the stick to point to the same distant star, which is basically just pointing to the left from our point of view here, because the distant star is miles away on the scale that we're looking at here. So that's 1 sidereal day right there. And okay, so anyway, that's 1 sidereal day. Now, if we keep track of what's happening relative to the sun, we have not even actually reached midnight yet, because you see we start at noon, and then if we think about what's happening at this point on Mercury, the sun is just setting right here. If you imagine yourself staying at that point on Mercury, the sun would be on the horizon right there. So the sun is just setting, and now it's nighttime on Mercury in that spot, but we haven't even reached midnight yet until we've completed 1 full year of orbit. Because now the stick is pointed away from the sun, so that's midnight. It took 1 full year to go from noon to midnight at that point on Mercury. Now, if we keep track of the sidereal days, the next sidereal day is completed right there, because the stick is pointed to the left. And then, if we let the rotation continue, we end up with the stick pointed back at the sun, which means that this is now 1 solar day since we started out. We started at noon, now here we're back at noon again, right? Because the sun is right overhead. And this has taken 2 full years of orbit, so it's 176 of our days, right? We usually index things to our days. So it's 176 days since we started the process, which is 2 full years on Mercury, because Mercury's year is 88 of our days, right? So this is 2 full years since we started. We have just achieved 1 solar day since we started. So we get this crazy situation where a solar day on Mercury is equal to 2 of its years, right? And moreover, if we keep track of how many times the stick was pointed to the left, it was a cycle of 3 times. So this is 3 sidereal days. So this is exactly why we had this idea that 3 of the Mercury sidereal days equals to 2 of the Mercury sidereal years. And we can also say it's equal to 1 solar day on Mercury. All these things are related by this pattern. And again, this can't be a coincidence. There's got to be a physical force that keeps this happening, and it's that gravitational traction on the caloric basin I was talking about. So this is just a summary of what I was just talking about. And so again, we find that 2 years on Mercury corresponds to just 1 solar day, but 3 sidereal days on Mercury. And so this is a 2 to 3 spin orbit resonance, because we look at the 2 Mercury years and the 3 days. That's where the 2 to 3 ratio comes from. Okay, so again, the point of that is that it's reinforced by the fact that there's this massive blob at the caloric basin, and that points to the sun. Well, the caloric basin is at perihelion at noon, so we get the gravitational force of the sun exerting this strong tidal effect that reinforces that resonance. All right, so just briefly to review, again, surface temperature variations are huge on Mercury because it is very close to the sun. So the nighttime temperature on Mercury is actually similar to the nighttime temperature on Earth, on the moon, about 100 kelvins. But it's over 600 kelvins at noon on Mercury. And this is just due to the same balance between infrared cooling and solar heating that creates the surface temperature on Earth. It's exactly the same idea, but of course we have much stronger solar heating, so we have a higher equilibrium temperature. And so we have a much more extreme variation of temperature on Mercury than we do on the moon. If we put the moon where Mercury is, then we'd see the same kind of temperature variation that we see for Mercury. This all has to do with the distance from the sun. And let's see. And then the final point is that, again, if we talk about the caloric basin, then what we find is even the larger temperature variation up to about 700 kelvins at the caloric basin, simply because the caloric basin is one of the 2 spots on Mercury which actually faces the sun at noon at perihelion. So remember, perihelion is closest approach to the sun. Perihelion is when the planet is closest to the sun. So if you have noon at the spot that you're at, and that noon occurs during perihelion, then you're going to have the strongest possible solar heating because your distance to the sun is minimized. Now I said it's one of two places on Mercury that actually is at perihelion at high noon. Okay, so there's one of two places. What's the other place on Mercury that also can be at perihelion during high noon? On the other side? Right, exactly. It's just the point on the other side. Because remember that if we think of this progressing around, if we have perihelion if we have high noon at the Polaris Basin, 1 year later, okay, Mercury will have flipped around 180 degrees, so the Polaris Basin will now be having midnight. It'll be on the other side over here, it'll be having midnight, and the point opposite from the Polaris Basin will be experiencing high noon. So it's a flip, flip, flip back and forth between those 2 points. But no other points ever have high noon during perihelion. So those 2 points are the points that are the hottest ones. And again, because the Polaris Basin faces the sun during perihelion, this massive blob that we think is there is actually the thing that the sun seems to be grabbing hold of to reinforce that 2 to 3 in orbit resonance.